Before rifling, there was smooth metal, a straight tunnel through a barrel, no spiral, no twist, just a hollow cylinder designed to contain pressure and release it forward. The musket dominated for centuries, not because it was precise, but because it was practical. From the 16th through the early 19th century, the smoothbore musket became the standard infantry firearm across Europe and much of the world. It evolved from earlier arquebuses and matchlock guns, gradually becoming longer, stronger, and more standardized. But inside the barrel, nothing guided the projectile. It was smooth. When a musket fired, a spherical lead ball traveled down the barrel, pushed by expanding gases from ignited black powder. The ball did not spin in any controlled way. It bounced slightly within the bore, especially if the fit was loose, which it usually was. This looseness was intentional. Black powder fouled the barrel quickly. After only a few shots, residue accumulated. If the ball fit too tightly, loading would become extremely difficult after repeated firing. Soldiers needed to reload quickly and repeatedly, often under stress. A slightly smaller ball wrapped in paper cartridge allowed faster loading. Speed mattered more than precision. The typical loading process required biting open a paper cartridge, pouring powder down the barrel, inserting the ball with the remaining paper as wadding, and ramming it down with a ramrod, then priming the pan. In flintlock muskets, or placing a percussion cap in later versions. Every step took time. Even in well-trained armies of the 18th century, a rate of fire of 3 shots per minute was considered efficient. Accuracy, however, was limited. A smoothbore musket firing a round ball was reasonably effective at short ranges, perhaps 50 to 100 meters for aimed fire. Beyond that, accuracy declined rapidly. The ball's trajectory was influenced by small inconsistencies in powder charge, barrel fouling, and imperfect sphere shape. The ball did not spin in a stabilized way. Without spin, air resistance could cause unpredictable drift. The projectile might veer slightly left or right. Over longer distances, this variability increased. Range was not irrelevant, but it was secondary to formation tactics. Armies compensated for limited accuracy by firing in volleys. Lines of soldiers discharged simultaneously toward opposing formations. The expectation was not that each individual shot would strike precisely, but that collective fire would produce effect through volume. The musket was engineered around this doctrine. It was relatively simple. It was durable. It could be produced in large numbers. Barrels were smooth because rifling, the cutting of spiral grooves inside the barrel, was labor-intensive and expensive in earlier centuries. Cutting precise helical grooves required skill and time. Smoothbore barrels could be manufactured more quickly. Logistics shaped design. Governments needed tens of thousands of muskets. Simplicity reduced cost and eased maintenance. Replacement parts could be standardized more easily when barrels required only boring, not intricate internal cutting. There was also the matter of loading speed. A smoothbore musket allowed a ball slightly smaller than the bore diameter to be rammed quickly down the barrel. Rifled barrels, by contrast, required tighter-fitting projectiles to engage the grooves. In early rifled firearms, loading was slower because the ball had to be forced into the rifling to achieve spin. For infantry formations emphasizing coordinated volleys, speed of loading outweighed the advantage of individual accuracy. The musket was not inaccurate in the sense of randomness. At close distances, it could be reliable, but its design did not prioritize precision over distance. It prioritized repeatability within formation. The barrel was long, often over 1 meter, which increased muzzle velocity by allowing expanding gases more time to accelerate the projectile. But even with length, without rifling, stability in flight remained limited. Environmental conditions added variability. Humidity affected powder performance. Wind influenced trajectory. Black powder smoke quickly obscured visibility after repeated volleys. Fields of battle in the 18th century often became enveloped in thick white smoke within minutes. Inside that smoke, precise targeting was nearly impossible. The musket's smoothbore design matched the tactical reality of its time. Engagement at relatively close ranges, coordinated group fire, an emphasis on discipline rather than individual marksmanship. Hunting communities, however, began to experiment with alternatives. In certain regions, particularly parts of Germany in the 15th and 16th centuries, gunsmiths explored the idea of cutting spiral grooves inside barrels. These grooves would impart spin to the projectile, stabilizing it in flight. But before that innovation spread widely, the smoothbore remained dominant. It was not a technological failure. It was a compromise. Manufacturing limits, powder chemistry, military doctrine, and economic constraints shaped its design. The spherical ball was easy to cast in molds. Lead was malleable and widely available. Paper cartridges simplified loading. Smooth barrels reduced friction and allowed faster ramrodding. Everything about the musket favored speed and scale. Accuracy was acceptable within expected ranges. Beyond those ranges, engagement was less about individual aim and more about coordinated presence. The smooth interior of the barrel reflects a stage in firearms history where control of explosion mattered more than control of trajectory. The primary engineering challenge was containing pressure safely and reliably. Refining the projectile's flight path would come later. In many ways, the musket represents stability. It remained largely unchanged in principle for over 2 centuries. Ignition systems evolved from matchlock to flintlock to percussion cap, but the barrel's interior remained smooth. This continuity suggests satisfaction with its performance relative to context. Only when technological advances and shifting tactical needs aligned did rifling begin to replace smoothbore systems on a large scale. Until then, the musket stood as the standard. Long wooden stock, iron barrel, simple lock mechanism, round ball, smoke drifting after discharge. Its limitations were known. Its strengths were sufficient. Range was not ignored, but it was not optimized for extreme distance. Effective engagement distances reflected realistic expectations of powder, projectile, and visibility. In this era, firearms were tools of formation and discipline. Individual precision, while valued in hunting and specialized roles, was not the primary design driver for infantry arms. The smoothbore musket embodied the technological plateau before refinement of internal ballistics became central. Inside the barrel, there was no twist, no spiral path guiding the ball, only a straight channel. Pressure building, release, sound, smoke, and a projectile traveling forward without spin carried more by momentum than by stabilization. It was a beginning, not yet shaped by the spiral that would define the rifle, but stable within its own limits. A smooth interior reflecting a time when engineering focused first on containing fire, and only later on guiding it with precision. Germany, late 15th century. Workshops in regions such as Nuremberg and Augsburg, where metalworking traditions were already well established. Barrels were being forged, bored, and polished by hand. Gunsmiths understood how to shape iron into a tube capable of containing explosive pressure. But inside those tubes, something began to change. Not on the outside, inside. Spiral grooves. The exact origin of rifling is not tied to a single documented moment, but evidence suggests that by the late 1400s and early 1500s, gunsmiths in the German states had begun experimenting with cutting helical channels into the interior surface of gun barrels. At first, these grooves may not have been intended to spin the projectile. Some historians believe they were introduced to collect fouling, residue from black powder that accumulated with each shot. By carving shallow grooves, fouling had space to gather, allowing the projectile to seat more consistently even after repeated firing. But whether intentional or accidental in origin, a physical principle became clear. When a projectile is forced through a spiral path, it rotates. Rotation changes flight. Inside a rifled barrel, grooves and raised lands, alternating ridges, create a twisted interior surface. When a tightly fitting projectile travels down this bore under expanding gas pressure, it engages the grooves and is compelled to spin along its longitudinal axis. This spin produces gyroscopic stability. The physics is simple but profound. A spinning object resists changes to its orientation due to conservation of angular momentum. When a projectile rotates rapidly in flight, it maintains a more stable forward-facing orientation. It is less susceptible to tumbling or random deviation caused by air resistance. Without spin, a spherical ball relies solely on its shape and momentum. With spin, even elongated projectiles can remain stable over long distances. In the early centuries of rifling, however, projectiles were still spherical. Even so, the addition of spin improved consistency. The rate of twist, how quickly the grooves complete a full revolution inside the barrel, determined the rotational speed imparted to the projectile. Early rifles typically had slow twist rates, appropriate for round balls rather than elongated bullets. Cutting rifling grooves required precision. Gunsmiths used specialized tools known as rifling benches. A long rod with a cutting head was inserted into the barrel. By guiding the rod along a helical path while gradually deepening the cut, craftsmen formed spiral grooves. Each pass removed only a small amount of metal. The process was slow, labor-intensive, expensive. Unlike smoothbore barrels, which required boring and polishing, rifled barrels demanded additional skilled labor. This cost limited early adoption. Rifled firearms appeared first among hunters and specialized marksmen, rather than mass infantry. In the forests of Central Europe, accuracy at longer distances mattered more than rate of fire. A hunter might fire once, carefully aimed, rather than multiple times in formation. For such use, the advantage of spin-stabilized flight outweighed slower loading times. Because early rifled barrels required tight-fitting projectiles to engage the grooves, loading was more difficult. The ball had to be wrapped in cloth patching and forced into the barrel with firm pressure. After several shots, powder fouling made loading even harder. Thus, rifles were precise but slow. The internal spiral changed the relationship between barrel and projectile. Pressure from ignited powder forced the ball into the grooves. As it traveled down the bore, Friction between projectile and rifling transferred rotational energy. By the time the projectile exited the muzzle, it was spinning rapidly, sometimes thousands of revolutions per minute. Once airborne, this spin stabilized its trajectory. Air resistance acts unevenly on non-spinning objects, causing wobble and drift. A spinning projectile maintains axial alignment. It cuts through air with greater predictability. The result was not infinite accuracy. Black powder still produced variable pressures. Wind still influenced flight. Sight systems remained rudimentary. But compared to smoothbore muskets, rifled firearms could achieve meaningful accuracy at significantly greater distances. This did not immediately revolutionize military practice. Armies valued speed of loading and simplicity of logistics. Rifles required more maintenance, more training, and more time between shots. Their benefits were situational rather than universal, but the principle had been established: spiral inside the barrel, rotation, stability in flight. The rifle, as a concept, was born not from desire for rapid fire, but from desire for controlled trajectory. In the 16th and 17th centuries, German and later Swiss and Austrian rifle makers refined the craft. Hunting rifles, often called Jaeger rifles, featured shorter barrels and larger calibers than later long rifles, optimized for woodland use. These firearms demonstrated that rifling was not experimental novelty. It was functional. The grooves varied in number and depth. Some barrels had 6 grooves, others 8. The geometry differed by maker. Each rifled barrel bore subtle variations, reflecting the hand of its craftsman. Physics, however, remained consistent. When a projectile spins, it resists tipping. The same principle governs spinning tops and gyroscopes. Angular momentum stabilizes orientation. In flight, this reduces deviation and improves predictability. The introduction of rifling marked a shift in engineering focus. Earlier firearms prioritized ignition reliability and pressure containment. Rifling introduced internal ballistics as a field of attention. How the projectile behaves inside the barrel and how that behavior influences external flight. The smooth interior of the musket was easier to produce. The spiral interior of the rifle was harder, but more precise. Precision required patience. Rifling benches occupied workshops for extended periods as craftsmen carefully deepened grooves. A mistake could ruin the barrel. Yet despite the effort, rifling spread gradually. In colonial North America, German immigrants brought rifling techniques that influenced the development of the American long rifle in the 18th century. These long-barreled firearms became known for their accuracy at distances beyond typical musket range. Still, the focus remained physics rather than speed. The rifle did not increase firing rate, it increased consistency. Each shot required more care, more time to load. But when fired, the projectile followed a more stable path. The spiral inside the barrel did not change the violence of combustion. Powder still ignited, gas still expanded, pressure still propelled. But the projectile no longer left the muzzle ungoverned by rotation. It left spinning, aligned, stabilized. The concept would later support elongated bullets, higher velocities, and modern ballistic science. But in its early form, rifling represented a subtle refinement, an internal twist, invisible from the outside, transforming straight travel into rotational stability. Germany, 15th to 16th century. Metal carved with spiral intent. A quiet adjustment inside the barrel that altered the relationship between fire and flight. Not louder, not faster, but more controlled. a change defined by physics rather than spectacle. And once the spiral proved its value, the smoothbore's dominance began, slowly, to recede. Early hunting rifles did not belong to formations. They belonged to forests, to hillsides at dawn, to a single figure standing still, waiting. In the German-speaking regions of Central Europe during the 16th and 17th centuries, rifled firearms became closely associated with hunting rather than warfare. These rifles, often referred to as Jäger rifles, from the German word for hunter, were designed for deliberate, aimed shots in the wooded terrain. They were not long by later standards. Jaeger rifles typically had shorter barrels than the muskets of their time. Their calibers were often larger, firing substantial lead balls capable of taking medium to large game. The emphasis was on reliability and accuracy at moderate distances, not on extended range or rapid fire. The rifled barrel inside these weapons imparted spin to the projectile, improving stability in flight. In dense forest, where lines of sight were interrupted by trees and brush, precision mattered more than volume. One shot, measured, considered. The loading process reflected this deliberate pace. A lead ball was wrapped in a greased cloth patch. The patch served two purposes. It sealed gases behind the ball to maximize efficiency, and it ensured engagement with the rifling grooves. The shooter placed the patched ball at the muzzle and used a ramrod to press it firmly down the barrel. The fit was tight. Unlike smoothbore muskets, which allowed loose-fitting balls for speed, rifled hunting rifles demanded close contact between projectile and grooves. After several shots, powder fouling accumulated and made loading progressively harder. Cleaning between shots, or at least careful ramrodding, became part of routine. This slowed the rate of fire. But speed was not the objective. The hunter did not stand in a line of 50 others. He stood alone, breath steady, the forest quiet. Ignition systems evolved over time, from matchlock to flintlock and later percussion cap. But the essential rhythm remained: prime, cock, aim, squeeze, flash, smoke drifting slowly between trees. The sound of a single report dissipating into open air. In the 18th century, the rifled hunting tradition crossed the Atlantic, with German immigrants settling in Pennsylvania and surrounding regions. There, the design evolved further into what became known as the American long rifle, often popularly called the Kentucky rifle. The American version extended the barrel length significantly, sometimes over 40 inches. This increased muzzle velocity by allowing expanding gases more time to accelerate the projectile. The longer sight radius also improved aiming precision. Calibers tended to be smaller than European Jaeger rifles, reflecting adaptation to available game and material constraints. Smaller calibers used less lead and powder, making them economical for frontier conditions. The long rifle became known for accuracy at distances greater than typical musket range. But again, the emphasis was not rapid fire. Loading required care. The patched round ball had to be seated properly. The flint had to be sharp. The priming powder had to be dry. In damp woodland environments, maintaining dry powder was constant concern. Hunters carried horn containers tightly sealed. The lock mechanism required periodic inspection. The rifle was as much a tool of patience as of mechanics. Its longer barrel made it less suited to tight formation maneuvering. It was carried over the shoulder, cradled carefully, or leaned against a tree trunk while the hunter paused. Unlike the musket, which often relied on massed volleys, The hunting rifle depended entirely on individual accuracy. There was no redundancy, no second-rank firing behind. A missed shot might mean hours of waiting lost. Physics governed its advantage. The rifling spiral imparted spin, stabilizing the ball in flight. Though still spherical in most early designs, the spinning projectile traveled with greater consistency. Wind drift remained a factor, but deviation was reduced compared to smoothbore fire. The trajectory of a round ball was still arcing rather than flat. Black powder limited velocity compared to later smokeless propellants. Yet within its effective range, the rifle offered control. The silence of the forest amplified everything. The metallic click of the cock being drawn back sounded louder in still air than it might on a battlefield. Hunters learned to move slowly, minimizing unnecessary sound. The rifle became an extension of quiet observation. When fired, the smoke cloud was thick and white, lingering between trees before thinning. In the moments after discharge, visibility could be temporarily obscured. The hunter often waited, listening rather than moving immediately. Maintenance was constant. After each outing, barrels were cleaned to remove fouling. Oil was applied to prevent rust. Wooden stocks were inspected for cracks caused by moisture. These rifles were personal possessions, often crafted with care and sometimes decorated subtly with engraving or brass inlays. They were not standardized military issue. They reflected regional styles and individual preference. The American long rifle in particular became associated with frontier life. Its long, slender form contrasted with the heavier military musket. The stock often curved gently at the butt, designed to rest comfortably against the shoulder. Despite later mythologizing, its primary role was practical, hunting for sustenance. The pace of its use remained slow. Powder poured, patch placed, ball seated, ramrod returned. Prime the pan, cock the hammer, aim with deliberate breath. Trigger pressed smoothly. The rifle rewarded steadiness. It did not forgive haste. Unlike later repeating firearms, it offered no immediate second chance. Each discharge required full preparation again. This slowness shaped behavior. Hunters learned patience. They calculated distance carefully. They accounted for drop-over range. They understood that beyond certain distances, even rifled accuracy declined due to ballistic limits of round balls. The early hunting rifle represents a different philosophy from military arms of its time. Where the musket valued volume, the rifle valued precision. Where formations emphasized coordination, the rifle emphasized solitude. Inside the barrel, the spiral grooves worked quietly. Outside, the forest remained still. The relationship between shooter and target was measured in breath and calculation rather than collective movement. One shot, one moment of ignition, smoke rising slowly through trees, then silence returning. The spiral inside the barrel had found its natural environment, not on open fields, but in quiet woodland spaces where accuracy outweighed speed. Early hunting rifles demonstrate how technological refinement does not always spread first through armies. Sometimes it advances through individuals seeking control over distance. In those forests, the rifle became not a weapon of mass force, but an instrument of alignment between eye, barrel, and distant point. A single projectile, spinning, cutting through still air, then resting again against bark or earth, waiting for the next careful preparation. In the quiet, the rifle remained what it was designed to be: precise, deliberate, slow, and deeply connected to the physics of a spiral carved inside metal. Military adoption did not follow innovation immediately. The spiral inside the barrel existed long before it became standard in armies. For centuries, rifled firearms proved their accuracy in hunting and specialized roles. Yet large military forces continued to rely primarily on smoothbore muskets. The delay was not ignorance, it was structural. Armies operate differently from individuals. A hunter values precision above all. A military institution values scale, speed, supply, and uniformity. The first obstacle was reloading time. Early rifles required tight-fitting projectiles to engage the rifling grooves. A patched round ball had to be forced firmly down the barrel. After several shots, black powder fouling accumulated inside the grooves, increasing resistance. Loading became progressively more difficult. In controlled conditions, this was manageable. In formation, under pressure, with hundreds of soldiers reloading simultaneously, slower loading reduced overall firing rate. Smoothbore muskets allowed looser-fitting balls wrapped in paper cartridges. Soldiers could ram them quickly, even when barrels were fouled. 3 shots per minute was achievable for trained infantry. Rifles often reduced that rate significantly. Rate of fire mattered in formation tactics. 18th century warfare emphasized coordinated volleys. Lines of soldiers fired in sequence to maintain continuous pressure. The effectiveness of this method depended less on individual precision and more on collective rhythm. If rifles slowed that rhythm, commanders hesitated to adopt them widely. The second obstacle was cost. Rifling a barrel required additional labor. Each spiral groove had to be cut carefully using specialized tools. This increased manufacturing time and expense. When governments needed tens of thousands of firearms, even small increases in cost per unit multiplied significantly. Smoothbore barrels were easier and faster to produce. They required boring and polishing, but not intricate helical cutting. Mass production favored simplicity. Before industrial machining reached high levels of precision, rifling remained partly artisanal. Uniform twist rates and groove depths required skilled craftsmanship. Variation between barrels could affect performance. Standardization is central to military supply. Uniform calibers allow ammunition interchangeability. Rifles, especially early ones, often had varied calibers and individualized bore dimensions. This complicated logistics. Logistics extends beyond production. Supplying ammunition in large quantities required reliable, interchangeable cartridges. Paper cartridges for muskets were simple to manufacture in bulk. Rifle ammunition often required patched balls prepared with care. Training soldiers to prepare and load these efficiently demanded additional time. Training itself was another structural factor. Rifles rewarded marksmanship. Effective use required practice in aiming, estimating distance, and accounting for trajectory. Muskets, used in mass formation, relied more on coordinated firing and close engagement ranges. Training an entire army to rifle-level marksmanship was resource-intensive. Time spent on marksmanship meant time not spent on drill, maneuver, and discipline. Armies prioritized systems. Smoothbore muskets fit existing doctrine. Rifles required doctrinal change. In some cases, specialized rifle units were formed. Light infantry and skirmishers adopted rifled weapons earlier than line infantry. These units operated differently, often dispersed, using cover, engaging at longer distances. But these were exceptions rather than replacements. For much of the 18th century, rifles coexisted with muskets rather than displacing them. Another consideration was durability. Early rifles, with deeper grooves and tighter fitting projectiles, could suffer more rapid fouling. Cleaning between engagements was essential. In prolonged campaigns with limited maintenance opportunities, reliability under harsh conditions mattered greatly. Smoothbore muskets, while less accurate, tolerated fouling better in the short term because their looser projectile fit reduced loading friction. Military adoption depends on predictability. Commanders need assurance that weapons will function consistently across thousands of soldiers under varied conditions. Rifles promise precision, but at the cost of complexity. The turning point did not come from doctrine alone. It came from technological refinement. In the mid-19th century, innovations such as the Minié ball transformed the balance. The Minié ball, an elongated projectile with a hollow base, expanded upon firing to engage rifling grooves. This allowed easier loading, similar to smoothbore speed, while retaining the stabilizing effect of rifling. With this innovation, the structural barriers weakened. Loading time decreased. Accuracy increased. Logistical standardization improved. Industrial manufacturing also advanced during this period. Precision machining made rifling more uniform and cost-effective. Factories could produce rifled barrels at scale with greater consistency than earlier centuries. As production techniques improved, the cost differential narrowed. Military institutions respond to alignment between technology and structure. When rifling no longer significantly slowed rate of fire, when ammunition could be standardized, when training could be systematized, adoption accelerated. But for centuries before that alignment, armies chose smoothbore muskets, not because rifles were unknown, but because rifles did not yet fit institutional needs. Structure shaped decision, rate of fire, cost per unit, supply chains, training time, maintenance requirements. These factors outweighed pure ballistic performance. The history of rifle adoption demonstrates that technological superiority does not guarantee immediate implementation. Institutions move according to internal logic. The spiral inside the barrel offered better physics, but physics alone does not determine policy. Armies evaluate entire systems, production capacity, transportation networks, training infrastructure, battlefield doctrine. Until rifled firearms aligned with those systems, they remained secondary. Gradually, as manufacturing improved and ammunition design evolved, rifling transitioned from specialist tool to standard equipment. But its acceptance was measured, slow, deliberate, shaped by budgets and logistics more than by demonstration of accuracy. Military adoption reflects structure. Structure resists abrupt change. Only when precision became compatible with scale did the rifle fully replace the smoothbore. Before that, the spiral remained present but peripheral, respected for its physics, yet constrained by the realities of organization. In the end, the shift was not dramatic. It was procedural, a gradual recalibration of supply lines, training manuals, and production floors. The rifle entered military standardization not through spectacle, but through alignment with structure. And once aligned, the smoothbore quietly receded into history. The turning point did not begin with a new rifle. It began with a new bullet. For centuries, rifling offered accuracy, but imposed a practical limitation: tight loading. A projectile had to fit snugly into the grooves to spin properly. That meant effort. That meant time. After repeated firing, Powder fouling inside the barrel made loading increasingly difficult. Armies hesitated because speed mattered. The solution did not come from abandoning rifling. It came from rethinking the projectile. In the 1840s, a French army officer, Claude-Étienne Minié, refined a design that would change the relationship between rifle and soldier. His bullet, later known as the Minié ball, addressed the central contradiction of early rifles: how to combine easy loading with effective engagement of rifling grooves. The design was simple but precise. Instead of a solid spherical ball, the Minié projectile was elongated and conical, with a hollow cavity at its base. It was slightly smaller in diameter than the bore of the rifle. This was crucial. Because it was undersized, it could be loaded quickly down a rifled barrel, even when fouled by previous shots. It did not require forceful ramming like earlier patched balls. But the key innovation occurred at ignition. When black powder ignited, expanding gases rushed forward behind the projectile. These gases entered the hollow cavity at the base of the Minié bullet. Pressure forced the thin lead skirt at the base outward. Expansion. The base flared. The bullet's outer surface expanded into the rifling grooves. In that instant, it achieved tight engagement with the spiral. The projectile began to spin. Thus, the Minié ball separated loading diameter from firing diameter. Loose when inserted, tight when fired. This solved the central engineering problem that had delayed widespread military adoption of rifled firearms. Loading time decreased dramatically. Accuracy increased significantly. The spiral inside the barrel could finally be used at scale without sacrificing rate of fire. The bullet's elongated shape also improved aerodynamics compared to a spherical ball. Even before the science of modern ballistics was fully formalized, the practical effect was clear: greater range and improved consistency in flight. Spin stabilized the elongated form. Stability improved trajectory, predictability. The Minié system aligned with institutional needs. A soldier could load quickly using a paper cartridge containing powder and bullet together. Tear cartridge, pour powder, insert bullet, ram, cap, fire. The procedure remained structured, but no longer required excessive force. Industrial production facilitated rapid distribution. Factories produced standardized bullets in large quantities. The hollow base design could be cast reliably using molds suited to mass manufacture. Rifled muskets, firearms combining musket form with rifled barrel, became viable for entire infantry units. This was not a dramatic redesign of the weapon's exterior. From a distance, rifled muskets resembled earlier smoothbores. The transformation occurred inside the barrel and inside the projectile. An engineering solution had reconciled physics with logistics. The spiral grooves could now be engaged without slowing the system. Governments adopted rifled muskets widely in the mid-19th century. The French model 1851 and later models integrated Minié-style ammunition. Other nations followed, incorporating similar expanding bullet designs into their own systems. The principle remained consistent: use gas pressure to expand the base and seal the bore. This also improved efficiency. By sealing the gap between projectile and barrel, expanding gases pushed more effectively against the bullet rather than escaping around it. Velocity increased relative to earlier loose-fitting designs. The improvement was not only in accuracy, but in consistency. Fouling remained a factor, as black powder still left residue. but the ease of loading allowed sustained use in structured formations without crippling slowdown. The Minié ball demonstrates how small geometric changes can produce large systemic effects. A hollow cavity at the base, thin lead skirt, gas expansion, engagement with rifling, spin stabilization. Each component of the solution addressed a specific limitation. The bullet expanded only when needed. It did not require mechanical alteration by the user. The physics occurred automatically at ignition. This automatic expansion represented a shift in design philosophy. Instead of forcing soldiers to adapt to the rifle's requirements, the projectile adapted to the rifle's structure. Engineering adjusted to human limitation. Mass adoption followed alignment. Once rifles could be loaded nearly as quickly as smoothbores while offering superior accuracy, institutional resistance diminished, training manuals updated, production lines adjusted, logistics standardized around new ammunition types. The smoothbore musket, long dominant for reasons of practicality, became obsolete in military service. The spiral inside the barrel was no longer peripheral. It was central. The Minié ball did not eliminate every challenge. Black powder smoke still obscured vision. Cleaning remained necessary. But the balance had shifted decisively. An engineering refinement inside a small piece of lead had unlocked the full potential of rifling for large armies. No new ignition system. No dramatic external transformation. Just a redesigned projectile responding to gas pressure in a controlled way. The bullet expanded. It sealed the bore. It engaged the grooves. It spun. And with that expansion, rifled firearms moved from specialized tools to standard military equipment. The turning point was not louder than previous innovations. It was more precise. A hollow space inside metal that allowed pressure to do the work. An elegant solution to a structural constraint. And once solved, the rifle's place in military systems became permanent. The next transformation in the history of the rifle did not occur inside the barrel. It occurred behind it, not in the spiral, but in the chamber, the bolt. By the late 19th century, the transition from muzzle-loading rifles to breech-loading systems was largely complete. Metallic cartridges, self-contained units combining bullet, powder, and primer, had replaced loose powder and separate projectiles. This alone simplified loading dramatically. But the question remained: how to feed, chamber, fire, and extract cartridges efficiently, reliably, and repeatedly. The answer was mechanical. The bolt-action system. At its core, the bolt-action rifle is defined by a rotating and sliding metal cylinder, the bolt that moves within the receiver. It performs several tasks in sequence: chambering a cartridge, locking the action, striking the primer, extracting the spent casing, and preparing the next round. The movement is deliberate. Lift, pull, push, rotate down. Each step corresponds to a specific mechanical function. When the shooter lifts the bolt handle upward, the bolt rotates slightly. This rotation unlocks locking lugs, solid protrusions at the front of the bolt, from corresponding recesses in the receiver. When locked, these lugs bear the pressure generated by firing. Unlocking them frees the bolt to move rearward. Pulling the bolt back extracts and ejects the spent cartridge case. A claw extractor grips the rim of the casing. As the bolt travels rearward, the casing is drawn from the chamber. Near the end of its travel, it strikes an ejector mechanism, flipping it out of the action. Push forward. The bolt strips a fresh cartridge from the magazine and guides it into the chamber. The magazine, typically located beneath the action, holds multiple cartridges under spring tension. As the bolt moves forward, it catches the top cartridge and drives it upward and into alignment with the chamber. Rotate down. Lowering the bolt handle rotates the bolt back into its locked position. The locking lugs engage solidly with the receiver, sealing the chamber. The firing pin inside the bolt remains under spring tension. When the trigger is pressed, the firing pin is released. It moves forward under spring force, striking the primer at the base of the cartridge. The primer ignites, powder burns, gas expands. The bullet travels down the rifled barrel. The bolt remains locked, containing pressure safely. The elegance of the bolt action system lies in its mechanical clarity. Each motion serves multiple purposes. Rotation both unlocks and locks. Linear motion both extracts and chambers. The Mauser system, developed in Germany in the late 19th century, became one of the most influential bolt action designs in history. Paul Mauser refined earlier concepts into a system known for strength, reliability, and controlled feeding. In the Mauser design, the extractor claw grips the cartridge rim as soon as it leaves the magazine. This controlled round feed ensures that the cartridge remains under mechanical control throughout its movement into the chamber. It reduces the likelihood of misfeeds or jams. The locking lugs at the front of the bolt engage deeply into the receiver ring, creating a strong lockup capable of handling high-pressure, smokeless powder cartridges. Unlike black powder, smokeless propellants generated significantly higher pressures, requiring stronger materials and tighter tolerances. Industrial metallurgy had advanced to support this. Steel production improved in consistency and strength during the late 19th century. Precision machining allowed receivers and bolts to be manufactured with repeatable dimensions. Interchangeable parts ensured that rifles could be assembled and repaired at scale. Standardization was essential. Military contracts demanded rifles that behaved identically across thousands of units. Bolt travel length, magazine capacity, caliber specifications, all were defined and replicated with industrial precision. The bolt action rifle fit institutional needs. It was robust. It functioned in varied climates. It tolerated dirt and debris better than more complex mechanisms of its time. Its operation was mechanical rather than automatic. The shooter manually cycled the bolt after each shot. This reduced mechanical complexity and enhanced reliability. Lift, pull, push, lock. The rhythm was deliberate but efficient. Compared to earlier single-shot rifles, bolt action systems increased sustained rate of fire without sacrificing strength. A trained soldier could cycle the bolt quickly while maintaining aim. Yet the system retained simplicity relative to later semi-automatic designs. The movement of the bolt itself is central. Inside the receiver, rails guide the bolt body smoothly. Cam surfaces assist in primary extraction, the initial breaking of the cartridge case free from chamber walls after firing. This mechanical leverage reduces effort. The handle provides torque. The lugs bear pressure. The extractor grips. The ejector clears. Each component has defined function. The Mauser Model 1898 exemplified these principles. It included a third safety lug, gas venting holes to redirect pressure in case of cartridge rupture, and a flag safety mechanism at the rear of the bolt to block firing pin movement. Reliability became engineering priority, not speed alone. The bolt action rifle bridged two eras: the era of deliberate single-shot precision and the era of repeating fire supported by magazines. It retained manual control. It emphasized strength. It relied on the operator to complete the cycle. The industrial context made this possible at scale. Factories produced millions of bolt-action rifles across Europe and beyond. Designs influenced one another. Variations appeared in Britain, Lee Enfield, Russia, Mauser, and elsewhere, each adapting core principles to national standards. Yet the mechanical logic remained consistent, a cylindrical bolt rotating to lock and sliding to feed, a firing pin under spring tension, a contained chamber aligned with rifled barrel. The focus was not spectacle, it was function. The movement of the bolt is quiet compared to discharge, a metallic click as it lifts, a sliding sound as it travels, a firm downward rotation signaling lock. These sounds define the system. The bolt-action rifle represents a maturation of mechanical thought. It integrates cartridge technology, metallurgy, and machining into a unified sequence. The spiral inside the barrel stabilizes the projectile. The bolt behind it controls pressure and repetition. Industrial standardization ensures that each unit behaves predictably. Lift, pull, push, lock, a closed system waiting for the trigger. And when at rest, the bolt handle lies angled downward, sealing the chamber. No motion, no pressure, only shaped steel aligned with intention. Mechanics ready, dependent entirely on the hand that moves them. Repeating rifles did not begin with speed. They began with storage, a place inside the weapon where more than one cartridge could wait. Before repeating systems, each shot required a full reset. Open the breech, insert a cartridge, close, fire. Efficient compared to muzzle loading, but still singular. One chamber, one round, one cycle. The repeating rifle introduced a magazine, a controlled space within the firearm designed to hold multiple cartridges under spring tension. The magazine changed the rhythm. Not automatic fire, not continuous discharge, but continuity between shots. The metallic cartridge made this possible. Earlier firearms relied on separate components: powder, projectile, primer. Even early breech loaders often required fragile paper cartridges or manually inserted caps. The metallic cartridge unified these elements: a brass or steel case, a primer at the base, powder sealed inside, bullet crimped at the front. When the firing pin struck the primer ignited the powder. Gas expanded. The case expanded slightly outward against the chamber walls, sealing it, a process known as obturation. This prevented gas from escaping backward. After firing, the case contracted slightly as pressure dropped, allowing extraction. The metal case performed several functions simultaneously. It contained, it sealed, it extracted, it standardized. The repeating rifle integrated cartridge and magazine into a mechanical sequence. Consider a lever-action rifle of the late 19th century. The shooter lowers the lever. This movement unlocks the bolt and draws it backward. As the bolt travels rearward, it extracts and ejects the spent casing. At the same time, the motion activates a carrier mechanism that lifts a fresh cartridge from the tubular magazine beneath the barrel. Closing the lever pushes the bolt forward again. The bolt strips the cartridge from the carrier and chambers it. Locking surfaces engage. The firing mechanism is cocked. The rifle is ready. One motion of the hand completes multiple tasks: extraction, ejection, feeding, chambering, locking. Repeating rifles varied in mechanism: lever action, pump action, straight pull, bolt action with internal magazine. But the principle remained consistent. a supply of cartridges under spring pressure, a mechanism that moves them into alignment with the chamber, a locking system that contains pressure during firing, a method of extraction and ejection to clear the chamber for the next round. The tubular magazine, common in early lever-action designs, stored cartridges nose to tail inside a tube, parallel to the barrel. A spring pushed them rearward toward the receiver. Later, box magazines, fixed or detachable, stored cartridges in stacked configuration. This allowed use of pointed bullets without risk of primer contact in the tube. The sequence remained mechanical, not automatic. The shooter had to cycle the action manually between shots. This preserved simplicity and durability. The rifle did not use recoil or gas to cycle itself. It relied on human motion. Speed increased, but control remained manual. The cadence changed. Fire, cycle, fire, cycle. The movement of the action became part of the rhythm of use. Mechanical feedback guided the hand, the resistance of springs, the click of locking lugs, the metallic sound of ejected brass striking ground. Industrial production supported this complexity. Manufacturing magazines required consistent spring tension and precisely shaped followers. Cartridges required uniform case dimensions to feed reliably. Chamber tolerances had to match cartridge specifications exactly. Standardization allowed interchangeability. Cartridges could be produced in vast quantities with predictable performance. Rifles could be designed around known dimensions and pressures. The metallic cartridge was central. Unlike earlier loose powder systems, it allowed the rifle to function as a sealed unit. No exposed priming pan, no external cap placement. Ignition occurred entirely within contained geometry. Primer struck, powder ignited, case sealed, bullet traveled, case extracted. This containment increased reliability and reduced environmental vulnerability. Repeating rifles did not eliminate pause, they reduced interruption. Instead of stopping to load after every shot, the shooter had a reserve. But the mechanism required deliberate operation. A lever thrown forward, a bolt drawn back, a pump slide moved along rails. Each system translated linear or rotational motion into internal alignment of components. The focus was sequence, each part moving in coordination. The magazine spring compressing and expanding, the bolt face engaging cartridge rim, the extractor gripping, the ejector striking, the next round rising into position. Repeating rifles transformed expectation. One rifle could sustain multiple shots without reload, yet the process remained structured. The shooter had to complete each cycle. There was no uncontrolled discharge, no continuous fire without input. This distinction defined the era. Repeating, not automatic. Industrial refinement improved durability. Hardened steel bolts resisted pressure. Stronger springs maintained feed reliability. Machined receivers aligned components with precision. The rifle became a system of linked movements. Magazine below, chamber central, bolt moving within, trigger releasing firing pin, cartridge igniting, extraction clearing, feeding repeating, each action dependent on the previous. When the magazine emptied, the rhythm stopped. The bolt cycled without resistance. No cartridge rose to meet it. The mechanical sound remained, but without ignition. Repeating rifles did not change the fundamental physics of rifling or combustion. They changed time. They shortened the interval between prepared shots. They allowed mechanical continuity without sacrificing manual control. Magazine, cartridge, metal case expanding and sealing, action cycling in defined order. speed without automation, movement guided by human hand, and when still, the rifle rests with magazine loaded or empty, spring compressed or relaxed, bolt forward or open, metal quiet, sequence paused, waiting for the next deliberate motion to begin again. Industrial precision did not change the rifle's purpose, it changed its consistency. By the late 19th and early 20th centuries, firearms production had moved fully into the industrial era. Workshops became factories, individual benches became assembly lines, steam and later electricity powered machine tools capable of cutting steel with repeatable accuracy measured in fractions of a millimeter. Precision was no longer dependent solely on individual craftsmanship. It was engineered into the process. Barrels were drilled using increasingly advanced boring machines. Rifling was cut, and later button rifled or broach rifled, with consistent twist rates from one barrel to the next. Tolerances tightened, variations decreased. Standardization of caliber became central. Earlier centuries saw wide variation in bore diameters. Even within a single army, dimensions could vary slightly from one firearm to another. Industrial manufacturing reduced these discrepancies. A defined caliber meant a defined cartridge. A defined cartridge meant predictable chamber pressures. Predictable pressures meant controlled performance. When governments adopted standardized calibers, 7mm, 8mm, .303, and others depending on nation, ammunition could be manufactured at scale and distributed confidently across units. Rifles produced in different factories could use the same cartridges without modification. Interchangeability became institutional. Bolt faces were machined to specific dimensions. Magazine wells matched cartridge length precisely. Barrel threads were cut to uniform pitch for consistent installation. Engineering documentation replaced informal measurement. Blueprints specified tolerances. Quality control inspected deviation. The rifle became not just an object, but a system governed by industrial standards. Smokeless powder, introduced in the late 19th century, further influenced design. Compared to black powder, smokeless propellants produced higher pressures, less smoke, and cleaner combustion. This required stronger steel and more precise chamber geometry. Metallurgy evolved alongside ammunition. Receivers were heat-treated to increase strength. Barrels were forged from improved alloys, capable of withstanding repeated high-pressure discharge. Industrial furnaces controlled temperature more precisely than earlier forges. Engineering became predictive rather than reactive. Ballistics emerged as formal science. Engineers studied projectile shape, velocity, air resistance, and trajectory mathematically. Wind drift and bullet drop were calculated rather than estimated intuitively. This knowledge informed barrel twist rates and bullet design. Optics entered the system. Early optical sights existed in limited form in previous centuries, but industrial lens grinding and precision machining made rifle scopes more viable and consistent. Telescopic sights mounted above the receiver allowed magnified sighting at distance. Mounting systems required alignment. Scope bases had to be drilled and tapped precisely into receivers. Rings had to hold the optic securely without shifting under recoil. Lens clarity depended on improved glass production and coating technologies. The addition of optics did not change the rifle's firing mechanism. It changed perception. Where iron sights required alignment of front post and rear notch, optics introduced crosshairs aligned with magnified targets. This enhanced effective use of rifled precision. Industrial precision also influenced ergonomics. Stocks were shaped using machinery that produced consistent contours. Butt plates aligned uniformly. Trigger pulls were calibrated to specific weights. Mass production no longer meant crude replication. It meant controlled repetition. Inspection protocols ensured uniform chamber dimensions. Headspace, the distance between bolt face and chamber shoulder, was measured carefully to prevent cartridge rupture or misfire. The relationship between cartridge and chamber became exact. Industrialization reduced variability in performance. Rifles of the same model behaved predictably from one unit to another. Military logistics benefited. Replacement parts could be shipped and installed without extensive fitting. Armorers followed standardized procedures. Maintenance manuals described exact specifications. Industrial precision extended beyond military use. Civilian rifles also adopted standardized calibers and precision manufacturing. Sporting rifles incorporated factory-machined receivers and barrels designed for consistent accuracy. Engineering evolution continued incrementally. Improved machining reduced internal friction in bolt movement. Better spring steel enhanced durability. Surface treatments reduced corrosion. Optics improved clarity and durability. The rifle became an integrated system of metal, cartridge, and glass. Factories, rows of machines cutting steel in synchronized rhythm. Gauge tools verifying dimensions. Inspectors measuring tolerances. Crates of standardized ammunition labeled by caliber and lot number. The individual rifle was no longer an isolated artifact. It was one unit in a network of production, supply, and design. Industrial precision did not eliminate human input. A trigger still required pressure. A bolt still required movement. But variability diminished. The spiral inside the barrel remained essential, yet now cut with mathematical consistency. Caliber standardized. Optics aligned. Engineering evolved, not through dramatic leaps, but through refinement of tolerances and materials. Each improvement reduced uncertainty. Each standard narrowed deviation. The rifle became more predictable, not louder, not necessarily faster, but more exact. Factories replaced workshops. Blueprints replaced intuition. Metal shaped by calibrated machines rather than by eye alone. And when assembled, the rifle reflected that evolution, a product of systematic engineering rather than singular craft. At rest, it appeared unchanged from distance. Barrel, receiver, stock, but inside, every dimension adhered to specification. Every surface machined to fit within defined limits. Industrial precision turned the rifle from a skilled instrument into a standardized mechanism, reproducible, measurable, and aligned with the expectations of modern engineering. The sniper rifle is not defined by speed. It is defined by distance, not by rapid sequence, but by control over trajectory. At its core, a sniper rifle is a refinement of the standard rifle, extended, stabilized, and aligned for precision at longer ranges. Its defining features are not aesthetic, but functional. A longer barrel, a carefully matched optic, and a design optimized for ballistic consistency. The longer barrel serves a clear mechanical purpose. When a cartridge ignites, expanding gases push the bullet forward through the bore. The longer the bullet remains inside the barrel, within safe limits, the more time those gases have to accelerate it. Increased barrel length generally results in higher muzzle velocity. Higher velocity reduces bullet drop over distance. It also shortens flight time. shorter flight time reduces the influence of environmental variables such as wind drift. The barrel is often heavier than that of a standard infantry rifle. This added mass reduces barrel vibration during firing. Every time a bullet travels down the bore, the barrel vibrates in subtle patterns known as harmonics. A heavier barrel tends to vibrate more consistently and with less amplitude, improving shot-to-shot predictability. Some sniper rifles use free-floating barrels, meaning the barrel does not contact the stock along its length. This prevents external pressure, such as grip or environmental changes, from altering barrel alignment. Consistency is the objective. The optic is equally central. An optical sight, or scope, magnifies the image of a distant target and provides a reticle, a set of crosshairs or calibrated markings, for precise aiming. Unlike iron sights, which require alignment of two mechanical references, a scope allows the shooter to focus on a single visual plane. Modern scopes include adjustable turrets that compensate for bullet drop and wind drift. These adjustments are measured in angular units, such as minutes of angle, MOA, or milliradians, MIL. By calculating distance and environmental factors, the shooter can adjust the point of aim to align with the expected point of impact. Ballistics governs this process. When a bullet leaves the barrel, it begins to slow due to air resistance. Gravity pulls it downward continuously. Even at high velocity, the projectile follows a curved path, an arc, rather than a straight line. The degree of drop depends on several variables: initial velocity, bullet weight, bullet shape, air density, distance, wind. Modern ballistic calculations use these variables to predict trajectory. Charts and software tools assist in determining how much to adjust aim at specific distances. Spin stabilization remains fundamental. The rifled barrel imparts rotation to the bullet. This spin stabilizes the elongated projectile in flight, maintaining its forward orientation. The rate of twist in the barrel must match the bullet's length and velocity to ensure proper stabilization. If the twist rate is too slow for a given bullet length, the projectile may not stabilize fully. If too fast, it may experience unnecessary stress. Barrel twist is therefore chosen carefully during design. The sniper rifle represents an integration of these elements. Long barrel for velocity and harmonic stability. Precision machined receiver for consistent lockup. High-quality trigger for controlled release. Optic aligned with bore axis. Stable stock geometry to support repeatable positioning. None of these components operate independently. The bolt locks. The firing pin strikes. The cartridge ignites. The bullet travels through rifling. It exits with rotational stability. It moves through air along a predicted arc. The shooter adjusts for environmental variables. Wind introduces lateral drift. A crosswind pushes the bullet sideways during flight. The amount of drift depends on wind speed, bullet velocity, and time of flight. Elevation adjustment compensates for gravitational drop. Temperature and altitude influence air density, which affects drag. All of this is physics. No acceleration beyond chemical combustion. No dramatic change in principle. Only refinement. Industrial precision supports the system. Barrels are often match-grade, manufactured with tighter tolerances and more careful inspection. Chambers are cut precisely to match cartridge dimensions. Ammunition may be selected for uniform powder charge and bullet weight. Repeatability matters. Each shot must behave similarly to the last. The sniper rifle is not inherently different in mechanism from other bolt-action rifles. The difference lies in tolerance and alignment. Triggers are often tuned for lighter, cleaner break. Stocks may include adjustable cheek rests and length of pull to fit the shooter precisely. Bipods or stable rests reduce movement. The objective is minimizing variables. The rifle does not eliminate physics, it works within it. Longer barrel, controlled ignition, spinning projectile, optical alignment, ballistic calculation. Distance becomes measurable rather than abstract. The rifle rests quietly before use, bolt closed, scope reflecting ambient light, no motion. When fired, the sound is singular. Recoil pushes rearward. The scope momentarily shifts, then settles. The bullet travels beyond visible distance. There is no spectacle in the mechanism itself, only sequence, ignition, acceleration, rotation, flight, descent, impact determined by physics rather than proximity. The sniper rifle represents the culmination of centuries of incremental refinement in rifling, metallurgy, cartridge design, and optics. It does not introduce a new principle. It refines existing ones. Longer barrel to maximize velocity, optics to enhance sight alignment, precision machining to reduce deviation, ballistic understanding to predict trajectory. Distance is no longer guesswork. It is calculated, and when unused, the rifle remains still, the barrel cool, the bolt closed, the optic clear, a system of aligned components waiting for deliberate input. Not dramatic, not automatic, only precise, governed entirely by mechanics and the laws of motion. Metal cools. After ignition, after recoil, after the internal pressure has dissipated and the bullet has long since left the barrel, the rifle returns to stillness. The barrel, which moments before contained expanding gases under high pressure, slowly releases its heat into the surrounding air. Steel contracts as temperature drops. The subtle expansion that occurred during firing fades back to its resting dimensions. There is no movement now. The bolt is closed. Its locking lugs remain engaged inside the receiver ring, but without pressure behind them. The chamber is empty or holds a cartridge, inert until struck. The firing pin rests under spring tension or relaxed, depending on position. Nothing advances on its own. The optic reflects ambient light. Glass surfaces gather small highlights from windows, lamps, or open sky. Inside the scope, lenses align precisely along a fixed axis. Crosshairs remain centered, unmoving. The adjustments made earlier, elevation, windage, remain set mechanically, but they do not calculate. They do not predict. They simply hold position. The magazine spring may be compressed beneath cartridges or relaxed if empty. It exerts quiet pressure upward, but without motion from the bolt. That pressure accomplishes nothing. The rifle lies motionless, stock resting against a surface, barrel supported, metal inert. Across its history, the rifle evolved through refinement of spiral grooves, cartridge design, bolt mechanics, and optical alignment. Each innovation reduced uncertainty. Each adjustment improved consistency, but none introduced autonomy. The rifle does not chamber itself. It does not align its own sight. It does not account for wind. It does not decide. Its internal systems are conditional. The firing pin will move only if released. The bolt will rotate only if lifted. The cartridge will ignite only if struck. In storage, the rifle is geometry and material. Steel shaped into cylinder and lug. Aluminum or wood shaped into support. Glass aligned in concentric tubes. Springs coil but inactive. Over time, oil applied to metal prevents corrosion. Surfaces remain protected through maintenance. Without care, Oxidation begins slowly at the microscopic level. Metal is stable, but not permanent. Even at rest, it interacts with environment. Dust settles, temperature shifts, humidity fluctuates. The rifle does not respond. It endures. In a safe, it remains closed. On a rack, it rests in alignment with others. On a table after cleaning, components may lie separated, bolt removed, chamber exposed, barrel inspected. Disassembled, the rifle reveals its dependence on assembly. Without bolt, it cannot lock. Without firing pin, it cannot strike. Without optic, it cannot magnify. Without cartridge, it cannot produce motion beyond recoil. Its power exists only in potential. Potential requires context. Mechanical systems do not act in isolation. They translate applied force into controlled outcome, but only when initiated externally. The spiral inside the barrel does not spin air. It spins only what passes through it, under pressure. The bolt does not cycle without torque. The optic does not choose a target. At rest, the rifle is quiet metal and glass. Balanced weight distributed along its length. Mass concentrated toward receiver and barrel. Center of gravity fixed. No sound except ambient air. In this state, it resembles what it fundamentally is, an engineered instrument designed to respond to input, not to generate it. Centuries of engineering have refined tolerances to fractions of a millimeter. Ballistic tables predict bullet drop to decimal precision. Optics calculate angular adjustment in minute increments. Yet when untouched, the rifle remains unchanged by those calculations. It waits, not actively, not consciously, but mechanically. Its condition is defined by readiness or storage, bolt closed or open, magazine loaded or empty, safety engaged or disengaged. Each state is static until altered. Metal cools, pressure equalizes, springs rest. The optic reflects light without distortion. It lies still. It does not act by itself. It waits for deliberate movement, a hand lifting the bolt handle, a finger applying measured pressure, a cartridge inserted into chamber. Without that sequence, nothing happens. The rifle's history is long, its mechanics precise, its physics predictable. But in silence, stripped of ignition and motion, it is simply matter arranged in alignment. Barrel forward, stock back, scope above, bolt within, motionless, waiting.